virtual course today. All right. Shall we start, Professor Baskoro?
Yeah. Okay. Please go ahead.
All right. Thank you, Professor Aditri Baskoro, already here. And thank you for the participant of the Internet Virtual Course attending these lectures today. I am Andi. I will be your moderator today. And our speaker will be Professor Aditri Baskoro, which is also my supervisor in ITB. How are you, Professor?
I'm fine. What about you?
I'm fine, thank you.
Okay.
Okay. The participant, now shall I read the curriculum vitae of Mr. Baskoro, Memprita?
Sure.
All right, thank you. Let me read Professor Edi curriculum vitae. Professor Edi Tribaskoro is a professor in Institut Teknologi Bandung, Indonesia. His work is in the area of graph Ramsey numbers, graph labelings, metric dimension, partition dimension, and located chromatic numbers, as you can see in the screen. His main research interests are graph theory and combinatorics for many years, and he is a pioneer in the development of graph theory and combinatorics community in Indonesia. For his leadership, he was elected as the president of Indonesian Combinatorial Mathematics Society since 2006 until 2013. And for his contribution to these fields, he was awarded by Habibie Award in Basic Science Research and Australian Alumni Award for Excellence in Education 2009. And also the award from Extraordinary Intellectual Quality Award in 2010. In education, as September 2022, he has 175 research papers, supervising 95 bachelor's, 51 masters, and also 28 doctoral students. Mr. Baskoro get his bachelor degree in ITB on 87 and his master and also his PhD from University of Newcastle, Australia. All right, ladies and gentlemen, let us welcome Professor Edi. Please. Oh yeah, yes. These are the selected publications from Mr. Baskoro, and the titles ranging from located metric dimension, Ramsey, minimal graphs, and also metric location domination number in graph theory. And today his lecture will be focused on Ramsey numbers. All right, shall we start the lecture, Professor?
Okay. Thank you very much.
Take your time. Yes. Have fun, everybody.
Okay. Thanks. Thank you, Pak Andi, for the introduction. And thank you, Dr. Prita, for the invitation to speak on this occasion. Okay, so I shall start sharing screen. Okay, let me see. Yeah. Okay, today I would like to introduce you to Ramsey minimal graph. Yeah. So we play around with this topic for today. Yeah. And we like to challenge you to find Ramsey minimal graph for certain properties, certain pairs. Yeah. Okay. This is our outline of the talk today. So of course I will give you some definition about Ramsey minimal graph. Yeah. and also some other terminology that related to Ramsey minimal graph. And then I give you few examples, yeah, to understand the notion of Ramsey minimal graph. And then I focus on the Ramsey minimal graph for matching, yeah. And I will give you some here some result, yeah, related to this Ramsey minimal graph for matching. And then this is another also a general property of Ramsey minimal graph for this particular pairs. Okay, I start with the definition. So suppose we have a graph G and H. You know, I think you know already graph, yeah, because I think Ibu Rinovia, yeah, already introduced you into a graph theory. So I believe you still remember what the graph is. Yeah? So given graph G and H, and we denote by this, yeah, F implies G comma H, yeah, means that in any red blue coloring on the edges, yeah, whenever I talk about the coloring, we always color the edges of the graph F, such that there is always a red copy of G or blue copy of H. Yeah. So this notation, yeah, means that whenever you color red and blue in any coloring, you know, on the edges of the graph F, you always have this particular subgraph with red, which is isomorph to G, and then or you have a blue copy of H. Yeah, either, yeah, one must be appear. Yeah, can be both or at least one. Yeah, at least one must be appear in this corresponding color. Okay, and I give you, this is one example. We have a cycle of on 8 vertices. So you have, this is actually, if I draw cycle here, how many here? Okay, another one. Yeah. So we have, this is C8. If you color by red and blue on the edges, yeah, no matter how you color these edges, you always have, this is, okay, the first one, the subgraph here, G here is, must be red, yeah. So G here is 3K2, yeah. And then H here is P3, yeah. So whenever you color by red and blue, you cannot avoid, yeah, to have either 3K2 in red, yeah, in red, or P3 in blue, yeah. Okay, okay. Why is that? Let's suppose, okay, this is, oh, actually this is the graph CH, yeah. Okay, why I draw no, here? Okay, I have a CH here, yeah, yeah, the cycle with 8 vertices, yeah. If you try to color by red and blue on the edges, let's suppose if I want to avoid 3 color this graph, this kind of graph. So, okay, I can color like this, for example. I color here, this is by red, and this is by red, yeah. And then, okay, you can continue if you want color, this one is also by red. Then, okay, this one and this one is already formed this layer. But to avoid that, okay, you cannot color another one, yeah. If you color here by red, then you have 1, 2, 3. Yeah. So if you color like this, then everything here must be blue, right? But if that case, then okay, you avoid this, but you will have here P3 with blue colors. Yeah. Yeah. Okay, let's try again. If I color like this, I want to avoid red. Yeah. So if I red 3 to K. Yeah. So I color this by red and by red here, and then I color red here, and this one red here, yeah, and also to avoid P3, yeah. But again, okay, we can. Sorry, if you color this thing, then you will have a P3, right? Yeah, this is P3, right? Yeah, because this is must be blue and this is must be blue again, yeah. So that means if you have 8 vertices on this cycle, then okay, no matter how you color by red and blue, you always have either this is 3K2 or blue with P3. Okay, and next, I will give you more definition. G, H coloring. Yeah, what we mean by G, H coloring is two coloring, red and blue, always using red and blue here, where we do not have a red G or blue H here in this color. Yeah. So here, suppose we have this graph. Yeah, this is graph path with 8 vertices. We have this graph with path with 8 vertices. If you color, this is by red, and this is also red, and this edge is blue, and this is blue, and this is blue. Yeah, then you can avoid to have red 3K2. Yeah, no red 3K2, right? Yeah, or you can also avoid blue P3. Yeah, yeah. So this coloring, we call it 3K2, P3 coloring on this graph. Yeah, on this graph. Yeah, or sometimes we call it a good coloring. Yeah, to make it shorter. Yeah, good coloring for these pairs. Yeah, for 3K2, P3. So that means you can avoid that. Yeah. Okay, so okay, this is two definition and two example. Yeah, and now I define what we meant by Ramsey minimal graph for a pair of G, H. Okay, graph F, we thought we always have without isolated vertices here. Yeah, graph F without isolated vertices is called Ramsey G, H minimal if satisfy these two conditions. The first condition is imply F imply G, H. That means if you color the edges in any coloring by red and blue, yeah, then you always have either red G or red H. Yeah. And this is because minimal. Then the second condition must be satisfied. If you remove one H from F, then this property no longer hold. Yeah. So that means if you remove one H, only one H in any H, yeah, yeah, this is must be any H, not only in one particular H. Yeah, you always have the property of the first one is no longer hold. So that means it's not implying G comma H. So that means if you remove one H, then you can find a labeling or sorry, coloring with red blue coloring with not implying red G nor blue H. Okay. And I'll give example here. Okay, before that, if I have this graph for particular pair G comma H, then I collect all the graph with this property. And we have, this is a family of all Ramsey minimal graph for G comma H. Okay. And Boer, Erdos, and Lawas in 1976, this is the first paper, I think, appear for Ramsey, graph Ramsey minimal, Ramsey minimal graph, saying that the problem of characterizing the family of RG comma H for a fixed pair of G comma X is a difficult question. Even though for very simple graph G and H, I will show later. We just select one very small graph, G and H, and then we try to find the family of Ramsey minimal graph for this particular pairs. And in this talk, I will consider the characterization from the simplest case here, whenever G or H is a T matching. Okay. Now I'll give you some examples about Ramsey minimal graph here. Okay. Let's suppose you have C5. Okay, because I want to color red and blue, so I have black color first in edges and vertices. Okay, this is C5. You have C5. And I want to show you that C5 is a Ramsey minimal graph for P3, P3. Okay, first I have to show you this is must implies P3, P3, C5. Okay, this is in red and this is in blue. Okay, now suppose you have any coloring, red and blue, in the edges, of the cycle of 5 vertices. If you color all edges are blue, then you have blue P3, right? So you cannot color by all blue. By all red also, okay, you always have red P3. So you have to choose these two colors, red and blue, But whenever you color here by red, then the edges incident to it cannot color by red, right? Because if you color by red here, you will have red P3. This is red P3. This is red P3, right? Okay, so let's see here. So if you have red edges, the red edges must be disjoint. So if this is red edges, then okay, this is might be red edges. Or if not, then probably this is must be red edges. And then you cannot have more red edges in this coloring, because whenever you introduce red edges here, then you will have red P3, right? But if you only have 2 red edges here, then this is must be blue, the color. This is also must be blue, and this is must be blue. So that means you will have, this is blue P3. Yeah. So if you avoid red P3, you will have blue P3. Yeah. So that means C5 is implies P3, P3. Okay. Is it clear? I just want to know the response from the student. Is it clear or no? Hello, hello.
It's clear, sir.
Okay, Nadia. Okay, Nadia. Nadia. Nur.
Yes, sir.
Rian.
Yes, sir.
Okay, clear, yeah? And now?
Yes, sir.
Yes, and now, thank you. I would like to prove that C5, if you remove one edges, will no longer satisfy this. So that means not implies anymore. P3, P3. Okay, let's have a look here. If you have C5 and then you remove one edges, you may select any edges here because the edges and the edge in C5 has the same role here. You can have any edges here. Okay, so let's suppose this is, you remove this edge, yeah. Okay, but if you remove that edge, then I can now color. This is by red, and this is by red, and this is by blue, and this is by blue. Now, by this coloring, yeah, I do not have red P3, and also I do not have blue P3, right? Okay, so that means, yeah, this is, you choose any edge here, yeah? And the edge here, if you choose this one, if you choose this one or this one, is the same, yeah? Because the graph that after removing, you have the same graph. Okay, so that means C5 is a Ramsey minimal graph for this P3, P3. Okay, yeah.
I'm sorry, sir.
Yeah.
There is several questions in the chat room.
Yeah.
So
okay.
Would you answer later on, or?
I couldn't see. Okay, I see here. Where is it? I have content both. Not necessary both. Yeah, of course. Okay, F here must contain both G and H before coloring. That's correct. Yeah. Otherwise, you just color by in the same color. Yeah. All the edges. Yeah. If F doesn't contain H, then color by blue or the edges. So that means safe. We save not having red G and also not having what is it? Blue G. Yeah, blue H. Yeah. So that means you never Ramsey minimal graph. So provided that's correct. Yeah, G and H must be inside F. Yeah, subgraph of F. Okay, and then what else?
Is there any restriction on G and H?
No.
There can be any kind of graphs, and there
can be any kind of graph. Yeah, as you like. Yeah, complete, not complete, anything, even disconnected as well. That's fine. Yeah. Okay. Or connected. Yeah. Okay, but okay, in the example I show you, matching is 3K2. Yeah, this is disconnected. Yeah, and then P3 is connected. Yeah. Okay, so okay, there is no restriction so far, but F here, yeah, the one that you have to find here, the Ramsey minimum graph must be having no isolated vertices. Yeah. Why? Because if you just put here isolated vertices C5 union K1, so if you just put this is dot, this is the isolated vertices dot and dot here, this is always happen. Yeah. Because the determination here is only by this graph. Yeah. Yeah. And then if you remove one edge, you remove one edge from this graph to this component. Yeah. So yeah, this is also happen. Yeah. So that means if you have C5 here is okay, satisfying the first condition and the second condition, and then you have in conclusion you have C5 is a Ramsey minimal P3, P3 minimal graph. Yeah. Then C5, yeah, union M K1, yeah, not K2. I saw that also Ramsey, but this is not minimal because the number of edges and the number of vertices is, yeah. Okay, so we're not allowed to have this one. Yeah. Okay. So we just count the this graph, yeah, without isolated vertices. Okay. Okay, so again, G and H, there's no restriction. Yeah. And then what else here? The edge should be deleted so that the graph stay connected. Not necessarily, yeah. Because this edge is always for any edge, yeah. So from this, yeah, from graph G, yeah, from graph F. Sorry. Okay. What else?
Sultan Ahmad, sir.
Huh?
The edge, we will get the P4, P4, P2, P2.
By removing
C4
edge,
is also P2, P2
which one?
from Sultan Ahmad
Yeah, yeah.
and Emilio Valerio.
No. If you only remove one edge, so you still have a P5, right? What do you mean by P4 here? Okay. And then what else here? CS, yeah, remove A. Then we get yeah. What do you mean by P? Yeah, we have P2 here. P2 here, right? So this is a P2 for blue. Yeah, this is another P2, and then this is P2, and this is P2. Yeah. Here is P3. Yeah. So it's no longer apply P3, P3. Yeah, not P2, P2. Yeah, P2, the same with this one. Yeah. So again, here, yeah, if you want to find the Ramsey minimum graph, the one that you have to show is the first one is here imply G, H, F imply G, H. This is NA, yeah, NA red blue coloring, yeah. And here, yeah, by removing one edge, yeah, this property is no longer whole, yeah, the same G, H, yeah. Okay, I think I should move on. Okay. Yeah. Next, is there any other Ramsey minimum graph for P3, P3? We have shown that C5 is yes, Ramsey minimum graph. Okay. Now my question is there any other Ramsey minimum graph for this pair? The answer is yes. What do you reckon? In fact, okay, if you take cycle with odd number of vertices, it's also Ramsey minimum graph. Yeah, the first here is C5, and now if you take, this is C2N. Again, I should have black one first. Yeah? Let's say here 2N plus 1. Yeah, vertices. Yeah. Then, this is will be applying. Yeah, P3, P3. Why is that? Okay. If you want to avoid red P3, and again, the edges, the red edges must be independent. So if this is already red, then you cannot have incident thread also red. Yeah. So this is must, okay, you can have this kind of red. And also you have this and so on. But because the number of vertices is, the number of edges is odd, then this is must be blue. Yeah. So you will have P3 in blue color. Yeah, this is also blue, it's blue, but you have, if you avoid red P3, then you will have blue P3. Okay, but if you have even number of cycle, that cycle with even number, let's say here, this is cycle with even number. Yeah, then you can color alternating. Yeah, this is red, 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 red. Yeah, and the remaining blue, blue, blue. Yeah. So C to N not implying P3, P3. Yeah. So C to N is not Ramsey minimum, not Ramsey minimum graph, but C2 cycle with odd number of vertices, will be Ramsey minimum graph for P3, P3. Yeah. Okay. Yeah. And then next question, any other? Can we have any other graph other than odd cycle? Sultan? Wah, ini Sultan Rafi. Yeah.
Sultan Ahmad, do you want to speak directly to Professor Baskoro?
Is there any other?
What, sir?
What do you guess?
Maybe Sultan Ahmad, do you want to speak directly? You can open your microphone.
Or Emilio? Fareha? No clue? Okay. Yes. This graph start with 3 edges. Yeah. This is will be implying P3, P3. Okay. If you avoid red P3, then you only have one red edges, right? you cannot have two. You cannot have two red edges. But once you have one red edges, then the remaining edges must be blue. So if you avoid red P3, then you will have blue P3. Yeah. So this star, yeah, this small star, yeah, imply P3, P3. But now, if you remove one, for example, let's say here, remove one here. I just make another one. Okay, oops, sorry. If you remove one, okay, edges, so this is the edge that you remove, yeah. Then, okay, you can color this is red and this is blue. So you have no longer this is implied to P3, P3. Yeah. So that means K1, 3 is Ramsey minimal graph for P3, P3. Yeah. Okay. And now, any other graph of this kind? So we have a cycles, yeah, with odd number of vertices. And then we have a star, 1, 3. And Emilio say here, C4 is also okay. P2, no, we are talking about P3, P3. So we focus on P3, P3 first, yeah? Okay. Yeah? Okay. And what else? Yeah. Okay. So, any other? The answer is no. Why not? Okay, I'll show you here. Okay, before that, okay, I'll show you that. Okay, the star, the small star, 1, 3, K1, 3 is Ramsey minimal graph, but this star with 4 edges is not Ramsey minimal graph for P3, P3. Yeah. Why? Because, yeah, if you remove, this is if you remove one edge, okay, but before that, is it this, does this graph satisfy in the first condition? Yeah, yeah, for K1, 4, yeah. If you color any by red and blue, yeah, in any coloring, you always have either red P3 or blue P3, yeah. Because if this is red, then you cannot have another red, yeah, to avoid red P3. So all must be blue, right? So that means it's, yeah, induce P3, yeah, in blue colors, yeah. But if you avoid blue color of P3, then you will have red color of P3, yeah. Okay, but this one, this graph is not minimal, because if you remove one edge, this one you remove, yeah, this edge you remove, then this is still imply P, P, P3, P3. Yeah. Yeah. So the second condition is not satisfied. So therefore, K1, 4 is not Ramsey minimal graph for P3, P3. Oh, yeah. Okay. Ijaz Jamil, what if we add odd number to n, like to n? Yeah. What do you mean, Ijaz? Is it? Hello, Ijaz. So I can.
Hello, Professor.
Yeah. What do you mean? I cannot understand your question.
Well, my question was, if what if we have odd numbers of vertices?
This is in cycle.
Yes.
Yeah, that's fine. Yeah, in cycle as always implies P3, P3. Yeah.
Okay, thank you.
Because all red edges, yeah, if you avoid red P3, so all the red edges must be disjoint. Yeah, must be disjoint. Yeah, but whenever you have the number of edges is odd, then you will have blue P3. Yeah, always blue P3, at least. Yeah, at least one. Okay, so it's no problem. So I conclude that if n is subgraph of f, then f is, yeah, that's correct. Yeah, if f is a Ramsey minimal graph, then any subgraph is not Ramsey. Any subgraph, yeah, because the second property must be satisfied. Yeah, the minimality. Yeah, the second property is the minimality. So if f is Ramsey minimal graph for particular pairs, yeah, G, H, then the subgraph of this graph of this f must not Ramsey minimal graph anymore for the same pairs. Okay, you're correct. Yeah, see, Juntong. Okay. So now I'm going to prove, yeah, only these two graphs, yeah, Ramsey minimal graph of P3, P3. Yeah. Okay. In fact, this was shown by Bohr, Edwards, and Lovaas. It's a long time ago. Yeah. Okay. So the proof is not so difficult. So let G be any graph. Yeah. Suppose G is a Ramsey minimal graph of P3, P3. Yeah. And since we already shown that this little star, yeah, K1, 3, yeah, is a Ramsey minimal graph for P3, P3. So this star is, we already shown that this is belong to that R, yeah, like Ramsey minimal graph for P3, P3. Then, yeah, if you have a graph F, or it is just G, yeah, then G is the maximum degree is at most 3, because if you have vertex with higher degree than 3, you have this kind. So you have a subgraph of this, yeah. So we'll violating the second condition, yeah. So will be not minimal for graph G. So that means G will be not Ramsey minimal graph anymore. So G, the maximum degree must be at most 3. Okay, so that means it's easy now. Yeah, you can have graph G with the maximum degree here is less than 3. Can be 3, can be 2, or can be 1. Okay. Okay. If the maximum degree. And now the only graph with maximum degree 3 is this star, yeah, because if we have graph G here, and there are one vertex with degree maximum, which is 3, then you cannot have other vertex anymore. Because otherwise, if you have this kind is connected like this, then this graph will contain, yeah, K13. We know already K13 is Ramsey minimal graph, yeah. So G must be not minimal anymore because contain the smallest one, yeah. So, yeah, if delta G is 3, we only have one graph, which is start with 3 edges. And now, yeah, we only deal now for the maximum degree is less than or equal to. So if the maximum degree G is less than or equal to, yeah, you have only few options here. Yeah, the first option is either path, for example, yeah, yeah, or cycle like this. Yeah, this is maximum degree 2. Yeah, or union cycle together with path. Yeah, mix, for example. Okay, so only this. Yeah. So the form, if you see the components of the graph G, this consists of cycle or path actually. Yeah. Okay, but if you have path, then is it possible to have path as a Ramsey minimal graph for P3, P3? Is it possible? This is implies if you color alternatingly by blue, red, blue, red, and so on. Yeah. So yeah, you will always have blue. I mean, all disjoint. Blue edges are disjoint, and also red edges are disjoint. So there is no red P3 and no no blue P3, right? So Pn never apply P3, P3. So Pn is not possible. Yeah? Only Cn. Okay, only Cn. Yeah. So only this kind of graph. The graph G is union of cycles. Yeah. Okay. And clearly, only in the odd cycle is belong to this graph. We already shown odd cycle is Ramsey minimal graph, yeah? But even cycle is not Ramsey minimal graph for P3, P3. Okay, so only these two graphs, yeah, satisfy P3, P3. Or we have Ramsey minimal graph for P3, P3. Okay. Now we go to another example. Yeah. Now we consider this pairs. Yeah, this pair 2K2, C3. Yeah, 2K2 is this graph. This is 2K2, and this is C3. Yeah, triangle. Okay, and we can show that K5 is a Ramsey minimal graph for this 2K2. Yeah, 2K2 and C3. Okay. Okay. Why that? We can easily show that. Okay. Take any red blue coloring. Any red blue coloring on K5. Yeah. And suppose that this coloring do not contain, oh, this is 2K2, sorry. Must be only 2 edges, yeah? 2K2, yeah. Suppose that this coloring do not contain red, 2K2, yeah? Yeah, so we don't have a red 2K2. And then we will show that this coloring must contain blue C. Okay. Yeah. So if this coloring does not have red 2K2, okay, then if you consider all the red edges on this graph, then these red edges will form either triangle or all red edges must be incident to one vertices, right? So in any coloring, I say it again here, in any coloring, red, blue coloring, yeah, which does not have red 2K2, then all red edges, yeah, will form either triangle like this or this kind of star. Yeah. You cannot have others. Yeah. Suppose, yeah. Why is that? Okay. Suppose if you have this is red one, yeah, then you cannot have this is red, right? Because we avoiding 2 red K2. We already have 2 red K2 here. So this is not possible. So if there are any red edges, then the red edges must be incident to either this or this. Yeah. So suppose this is another red edges. This is another red edges. Then if there are any red edges, other red edges, then yeah, can be here, yeah, form a triangle, or must be here, or must be here, yeah, and probably here, and so on, right? Okay. So suppose if you have this kind, yeah, then you cannot have red edges anymore, right? In this graph, if you have, this is 4 red edges incident to 1 vertex, yeah. So you cannot have red edges anymore in others, yeah, because we want to avoid red to K2, yeah. But if you have this situation, then you will have a triangle with blue edges. This is, oh yeah, this is the triangle, right? Oh, there's in fact many, not only one, yeah, in this situation, yeah. Okay, as long as I can have one, that's fine, yeah. Okay, yeah. Or the red, oops, I should remove all of them then. Just a moment. Or you have, this is all red edges form a triangle, or red edges form triangle, like the one that I already told you here. Yeah. But if in that case, then you still have a blue triangle, yeah, which is probably here or the other one, yeah. Okay, so if you avoid red 2K2, then you will have blue C3 for this graph. Okay, yeah. So here, I said in the earlier that whenever you color by red and blue, coloring, which does not contain red 2K, then the red edges will form a triangle, yeah, or will form a star. Yeah. So only two cases, yeah, will form a triangle or will form star. Yeah. So by considering any red blue edges, any red blue coloring, we can think of to remove, yeah. In the first case here, yeah, the red coloring here, the red edges here, can be considered as removing edges of this triangle in K5. Yeah. So if you remove this triangle, if you color this is by red, this is the same as you remove these edges and these edges and these edges. Yeah. And you will have, you still have a triangle. Yeah. Triangle in, yeah, in K5 here, yeah, after removing red edges. Yeah. Okay, so instead of you color, you can consider by removing this edges, this triangle. Yeah. Or in the second case, yeah, if you color by red and blue coloring, yeah, in any way, yeah, you may have this kind of pattern, which is red edges incident to one vertex. This is, we call it vertex X. Yeah. This means that if you remove this vertex, yeah, this one vertex, yeah. So you will have this graph, right? By removing one vertex, yeah, vertex X, yeah. When you remove vertex X, so you will have this. Okay, so the remaining here actually the edges that you color by blue, yeah. So okay, later, yeah, we will use this fact, yeah, to explore, yeah, the property of Ramsey minimal graph for this particular pairs. Yeah. Okay. So K5 is a Ramsey minimal graph for this pairs. And my question is, any other graph that also Ramsey minimal graph for this pair? The answer is yes. In fact, two cycle with three vertices is also Ramsey minimum graph, yeah, of this pair 2K2, C3. Okay. Yeah. Why then? If you want to avoid red 2K2, yeah, then again by the same the previous example, we know that red edges, yeah, here will form a triangle or star like this, yeah. Okay, either triangle or star. So if you color, this is one red, you cannot color in here by red, yeah. So the red one must be colored in the first component only. If you introduce one red in the first component, then all red colors will be there, yeah. So you have this example, yeah, and so on. But once you have that, then you will have C3 here. Okay, so you always have, okay, C3 and blue color if you avoid 2K2, yeah, in red. Okay, and then by removing one vertex, one edges, sorry, let's say here I remove one, yeah, and then I can color now, yeah. This is by red, and this is by blue, yeah. So I cannot have 2K2 in red and or C3 in blue, yeah, C3, yeah, not P3. Okay, so 2C3 is also Ramsey minimum. Okay. Any other? Yes. What else here? Okay. In fact, Bohr, Edwards, and Fodry, Rosso, and South show that this three graphs are the only Ramsey minimal graph. Yeah. So the one that I haven't proved is this one. Yeah. Okay. This is the only 3 Ramsey minimal graph for this pairs. Okay. And now I move to Ramsey minimum graph for matching. Yeah, we just consider only for matching. Okay. Okay, let's. So far, so good. Hello, hello. Are you still awake or?
Okay,
see.
students, is there any other question?
Sarah, Napitupulu, Sylvia, Siti Nur Aisyah. Oh, ada penyanyi kita ini. Siti Nur Halisa, ya, bukan Aisyah ya. Okay. Okay, it's clear? Yeah. Okay, good. Okay. Now, the pair G, H is called Ramsey finite or Ramsey infinite, depending on the cardinality, yeah, of the set R. Yeah. So if you have the set R can be infinite, can be finite. Yeah. So if the set is infinite, then the pairs we call it Ramsey infinite. Yeah. If the set is finite, then we call it this pair is finite, Ramsey finite. And Nestetter and Rodel in 1978 show that the pair G, it is infinite if at least one of the following holds. Okay, I will not prove this one. Yeah, if you are interested in knowing the proof, you just consult this paper. Yeah. Okay. So if one of these conditions satisfied, then the set of all Ramsey minimal graph that you look for, yeah, is infinite. Okay, so G and H are both tree-connected. Okay, so that means if you remove the number of edges is less than 3, this graph is still connected. And so this means tree-connected. Or the chromatic number of G and H is at least 3. So that means you need 3 colors, yeah, at least 3 colors to have a proper coloring of G and H. And then the second one, yeah, and then the third one, G and H are both forest, neither of which is a union of star. Okay, so if you have this, one of these, then the pair is infinite. So the set of all Ramsey numbers for this particular pair is infinite. Okay, this doesn't leave an obvious gap when G or H has connectivity 2 or less. It's not mentioned here. Yeah. So it's connectivity is 2 or 1. Yeah. And the part 3 is not satisfied. And also the part 3 here. Yeah, it's not satisfied. Special cases for graph which fit in this gap have been considered in several papers here. And in particular, if G is a matching, yeah, one of them is matching, G or H is matching, then we have this theorem from Bohr, Edwards, Fodry, and Shaw. If G is matching and H is any graph, yeah, then the pair of G comma H is finite. That means the number of Ramsey minimal graph for this pair G comma H is finite. Okay, and this is the conjectures. Still now is still not settled by both. Yeah, if the pair G comma H is Ramsey finite, yeah, then this one, yeah, is also Ramsey finite. So you add G with matching M2K2, and H here is also you add M2K2. It's also Ramsey finite. Or this is another conjecture. The pair G comma H is Ramsey infinite unless both G and H are star with an odd number of edges, or at least one of the G or H containing a single edge component. A single edge component is like this, yeah. So this is K2, yeah, actually. Okay. So the complete classification of this pair, G comma H, which are Ramsey finite, remain a major unsolved problem. Even finite is still difficult to find the classification of all Ramsey minimal graph for this pair. Okay. And in the remaining lecture, I will give you some two examples, big example here, yeah, to find or to characterize all Ramsey minimal graph of particular pair. The first pair is 2K2, comma TK2. Yeah. So this is 2K2 is this one matching with 2 edges, and TK2 is also matching with T edges. Yeah. Okay. So it's very simple graph. Yeah. But to find Ramsey minimum graph with for this part is not so simple. Okay. Okay. So this is the first part. Yeah. Okay. Now consider the classification problem for G is equal to K2, and then it is equal to K2. Yeah. In fact, this classification has been shown by Bohr, Edros, Self, Bohr, Fodry, Self, Edros, and Rosu in 1981. Yeah. Okay, probably you haven't born, yeah, in 1981. Okay. I was in that time. I was still in high school. Yeah, in the 12th class, yeah, 12th grade, yeah, 1981. Okay, it's clear, yeah. If you want to find K2H, yeah, so the set is only graph H, right? Yeah, is that clear? Yeah, because if you have graph H here, yeah, we'll always apply K2 comma H, right? So if you want to avoid having red K2, so that means there is no edges with red color, right, in this graph. So if there is no red edges, then all edges must be blue. So that means you will have a blue edge. Yeah? But whenever you introduce one edge in red color, then yeah, you will have red 2K2. Yeah. So that means H implies, yeah, K2 comma H. But when you remove one edge, yeah, when you remove one edge, yeah, with one edge, then it's no longer true here. Yeah, so it will not imply because you color all the edges by blue. Yeah, after you remove one edge, and then color this graph by blue. So you don't have a blue edge, and also you don't have a red 2K2, red K2. Sorry. Okay, so it's okay. This is trivial. Yeah, you have here K2 comma H contain only H because we look for the minimality. Yeah, so every graph which containing H is also imply, but it's not minimum. Yeah. Okay, so that means it's not Ramsey minimum. Okay, and now what about here? If you have 2K2 comma T K2, then okay, of course, this graph will imply. This graph is actually matching with T plus 1. That is this. Yeah. T plus 1 edges, sorry. Yeah. If you want to avoid 2K2 in red, then just color in any coloring here by red and blue, then you will have only one red, right? But if you add only one red, then the remaining will form the K2 in blue. Yeah. Yeah. So this is always implied. But now if you remove one edge here, if you remove one edge here, now you may color this one by red and the remaining by blue. Yeah? Then you will have T plus 1 K2 minus an edge will not imply this anymore. Okay. So clearly, yeah, T plus 1 K2 is belong to that set. Yeah. Ramsey minimum graph for 2K2, comma T K2. And now I consider, okay, this graph is disconnected, right? This graph, yeah. T plus 1, this graph, sorry. T plus 1 K2 is disconnected. So now I consider the other member of this set minus this graph. Yeah. Yeah. So I consider all the graph which is not T plus 1 K2. Okay. This is we call it the set R prime. Yeah. R prime to K2, comma T K2. Okay. Now we are going to study about this set. So F, if F is belong to this set, then if only if this is must be satisfied. Each one must be satisfied. Okay. The first one, the one that you asked in the previous time, you say that, okay, F must contain, yeah, T mentioned here, yeah. Okay, so, but even more, F here, the one that we are looking for, F here, must contain T matching. Yeah, and this matching is maximum. Yeah, if not, then never imply, right? Yeah, because F is Ramsey minimal graph of this one. Yeah, so if not, yeah, if this is not satisfied, yeah, so the matching is not maximum. Yeah, so T matching is not maximum. Yeah, so the maximum can be bigger than T. Yeah, then is this is will violating. Yeah, so it's not 2K2 comma K2 or the second one. Sorry. So F implies 2K2 comma K2, and then F minus E will not imply this one. Yeah. Okay. T matching must be maximal. Okay. They contain T matching. If not, we will violate either 1 or 2. In that case, it's 2 will be violate. Yeah, so it's not match, not minimum. And then the second property here, any vertex F, any vertex V, yeah, if you remove from F, will contain the matching. Yeah, this is because the first property. The first property said F must imply 2K2, comma T K2. Yeah. So that means if you have F here, Consider any red blue coloring of on the edges of F, and then if you avoid red 2K2, then all red will be form a triangle, or all red will be formed star like this. So if all red will form a star like this with center V, then by removing V here, because F implies 2K2 comma K2, so that means you will have T matching in blue. So you have T matching here, matching in blue. And then the third one here, the red one can be a triangle. So if the red one is triangle, like this, and the remaining edges must be blue, the remaining edges must be blue, Then because F implies 2K2 comma T-K2, so if there is no red 2K2, we will have blue T-K2, So that means F, by removing the red edges here, the red edges here form a cycle with 3 vertices, then we will have T matching in blue. So that means we have T matching in F. Okay. So this is the proof actually. So this property must be satisfied, and this is sufficient and necessary condition for F, being Ramsey minimal graph, a part of T plus 1 K2, T plus 1 K2 here, we're not included there, Okay, we treat it differently. Okay. So the proof is, I just explained, So whenever the edges of F here are colored by 2 colors, such that no red 2K2 as a subgraph, then the red subgraph must be a triangle, or cycle with 3 vertices, or form a star. So if the red subgraph is triangle, removing the edges, the red edges, means that we have this, F minus E C3. If you remove edges C3 and F, then here, in any color, and they said you have T matching in blue, right? So that means the graph contains T matching after removing C3. Or if the red subgraph is a triangle, a star, so you have this condition. F minus 3 contain T matching. Okay. And now, okay. What time is it? Okay. And now let's assume that we have F1, in this set, and F2 in this set, but with this is T1 and this is T2, So let's say I draw here. Okay, not using red one. Okay, I'll just like here, this is F1. Yeah, and this is F2. Okay. Yeah, and this is belong to 2K2, T1. And this one belong to 2K2, T2. Okay. Yeah, different, yeah, T1 and T2. But T1 plus T2 is equal T. Okay, it's not necessary. Yeah. And now I make a new graph, yeah, by using these two graphs, yeah, F1 and F2, yeah, by dot here, F1 dot F2. This is a graph from F1 and F2 by identifying a fixed vertex F1 with a fixed vertex F2. So let's, okay, suppose you fix here vertex F1, and this is another vertex F2. Then, yeah, you identify, you have like this, yeah. Okay, so this is the new graph. We call it this, yeah. Call it F1 dot F2. Okay. And then I will show that F1 dot F2 is in this Ramsey minimal graph. 2K2, comma, T1 plus T2K2. Yeah. Okay. Why is that? Okay. Remember here, F1 is Ramsey minimal graph of this kind, and then F2 is Ramsey minimal graph of this kind. So if you take any coloring, yeah, red blue coloring in this graph now, okay, and then suppose that in your coloring there is no K2 in red 2K2, yeah. Then if there is no 2K2 in red here, then you will have matching here with the number of T1 in blue, right? Because F1 is Ramsey minimal graph of this kind. Yeah. And now, okay, furthermore, if there is no 2K2 in red in F, then there is no 2K2 here. Yeah, there is no 2K2. Yeah, only one can be triangle or like this. Yeah, star. Yeah, but only one. Yeah, only one K2. Yeah, yeah. There is no two red edges, two independent red edges. Yeah. Okay. So in that case, because F is Ramsey 2K2 T2 K2 minimal graph, then we will have, this is a matching, yeah, with T2 edges. Yeah. So together with this, we will have T1 plus T2 blue matching. Yeah. So, okay, this one is implied, yeah. And now to find the minimality, yeah, to show the minimality, then right, so you remove one edge. Let's suppose this edge you remove, yeah, in F, yeah. I call it edge A, yeah. Then, because F1 is Ramsey minimal graph of this kind, so we can color in this graph, yeah. We're not considering the other one, in this color, in this graph, yeah, show that we have no red 2K2 here, and no, yeah, blue T1K2 here. So that means here, if you have matching, yeah, in blue, the matching here, the number of matching here is T1 minus 1 at most. Cannot be T1, yeah. And there is no red color. So now you can color this side by this coloring, and then you color this side, yeah, by having, yeah, no 2K2, yeah. So you only color either triangle, yeah, for red edges, or you have a star, yeah. So you just choose, yeah, you just make choice like that. Make a choice for this side. Okay. But if you do that, yeah, you will always have matching in blue with the number of edges is at most T2, yeah, because F is belong to this set, yeah. Okay, so, okay, by this coloring, you have no 2K2, yeah, in this graph, and also the number of blue mentioned is at most T1 plus T2 minus 1, not T1 plus T2, yeah. So it's less than T1 plus T2. Okay, so that means if you remove one edge, yeah, then it's not apply anymore. 2K2, T1 plus T2, K2, yeah. Minus A, yeah. But what about if you choose A is in F2? The same thing you can do, the coloring. Yeah. Okay, so we have proven that, sorry, that F1 dot F2 belong to this, yeah, and also the union, yeah. The proof is understand. If the union you have like this, yeah, disconnected, yeah, the graph, F, yeah, yeah. Okay, so it's the same. Okay, so you have this, then the converse of this result is also if you have this is the graph here, then you can, if the graph is this one, yeah, like this, then if belong to this one, T1 plus T2, K2, then this is must be T1, and this is must be T2, yeah. So the converse is the same. Or the union, if you have the union graph here, is belong to R 2K2, T1 plus, yeah, or you just say this is TK2, yeah. Then, okay, here, yeah, this graph, yeah, must be belong to R 2K2, T1 K2, and then this graph belongs to 2K2, comma T2 K2, such that T1 plus T2 is equal to. Yeah. Okay. And now let's F be a connected graph, and F is in this set. Yeah. Then we can show that F contains no bridges. Yeah. Bridges means, okay, this is an edge in graph F. We call it bridge. If you remove this edge from F, and then you will have two components, or the component is, the number of component is increased. Yeah. So suppose in the previous one you have F connected here, then this is an edge, is a bridge. If you remove this edge, then you disconnect the graph. Yeah. Okay. So this is, we call it bridge. Yeah. So if you have this has a bridge, so the situation is like this. Yeah. So this is an edge. We call it bridge here. Okay. So here we cannot have this kind of situation if F is belong to this graph. Okay, by using the three properties, yeah, the one in the previous one here. Here. Okay, F must contain T matching, which is maximum, and then if you remove one, okay, I'll just copy here. Okay. Huh? Oh, let's see. Sorry. Kok nggak mau? Oh, nggak. Oh, harusnya begini dulu. Oke. Okay. So, okay. Now I can make a copy here. Paste. Oh, sorry. Aduh. Nah, here. Okay. Yeah. So F must contain T matching as a maximum, and then if you remove any vertex, then they still have a T matching. And then if you remove any triangle, they still have a T matching. Okay. So suppose if, yeah, in graph F here, you have a matching. Yeah, sorry, you have a bridge here. Yeah. This is, we call it, okay, bridge. Okay, I'll just say here, this is X and Y. Okay. For that X and Y. Now, according to the above theorem, saying that F, this is F, yeah, content T matching is maximum. So here, yeah, F we have T matching. This is maximum. You cannot have T plus 1. Yeah. Okay. So consider this, yeah. And then now, if you remove X here, suppose if you want to remove X, okay. So if you remove X here, then this edges will be gone, right? And also this vertex is also okay. Just a moment. Okay, yeah. So this is the vertex X that you remove. And this is the edges incident to X. And probably you have also edges here and there. Yeah. Okay. And by this theorem, they say that if you have, by removing X, you still have F minus X contain dimension. Okay. So the dimension here will be distributed into two places. Yeah, the first place here, and then this is the second place here, because we have two components. Yeah, in the F minus, in the graph of F minus H. Yeah. And so let's say here we have S1 matching, and this is S2 matching. Yeah. After removing X. Yeah. And I can assume that this, yeah, must be involved vertex Y. Is that correct? Must be, yeah. Because if not, if the matching is like this, yeah, yeah, with S1, yeah, S2, yeah, S2 blue edges, yeah, yeah, and this is S1 here is S1, and then the one here is S2 here, yeah. If vertex Y is not in the end point of some vertex, some edges in S2, then what happened here? Here we have S1 plus S2 must be equal to, right? Yeah, because this property, yeah, by removing X, yeah, you have a T matching, yeah. So S1 matching in left side, and then S2 matching in the right side, yeah. And then if you add, you will have T. Yeah. But now suppose if Y, yeah, vertex Y here is not the end point of this edge. Yeah. Okay. If that happens, then now put it back the vertex Y, vertex X. So now this, yeah, if you put it again in F, then you have F, right? And now this edges, yeah, this edge X1 and edge X1 will be independent with this edge, the blue matching in the left side, and also independent with blue matching in the right side. So together with these two, we will have T plus 1 matching. Yeah. So violating the first property. So that means, yeah, we cannot have. So that means our assumption is wrong. This is the matching here must involve Y. Yeah, must involve Y. Okay. Yeah. Okay. So here we have S1 and S2, and S2 is must involve Y. S1 is no involving X, right? Yeah, because X you remove, yeah, from the F, yeah. So there is X here is not the endpoint of S1. Yeah, any edge in S1. Okay, now do it again. Yeah, by considering now the vertex that you remove is in right side. So here I just draw again. Now here full, this is X and this is Y, but you remove Y. Yeah. Okay. Yeah. So by removing Y, then according to property 2 as well, yeah, there will be matching, yeah. Here, some matching in here, and then another matching is here, yeah. Okay, and the number of the matching, yeah, is must be equal to, yeah. Okay, in the previous case, you have here S1 plus S2 equal T, you know? And then now you have here now, okay, in the previous case, S2 matching in the right side involving Y, yeah. And now here, this is, okay, I just call, let's say, what do we call it here? A P, you know? This is the number P1 and then the number P2. So you have P1 plus P2 is equal to, right? Yeah? Okay. So here, in the first case, yeah, you have S1 plus S2 equal T. And then in the second case here, we have P1 plus P2 is equal to as well. Yeah. But remember here, yeah, in the first one, Y here is involved in S1, S2, yeah. So this one is must be less, yeah. P2 is must be less than S2, and then P1 is must be greater than S2, yeah. Yeah. Otherwise, we cannot have T1. Yeah. Yeah. Okay. Yeah. So now we have. Let me see here. I said it. F P1 is greater than S2. Yeah. And then S1 is S2 is greater than P2. Yeah. And now put it back again. X and Y here. And now consider F. Yeah. So if you have this, yeah, then if you consider graph F, then the matching here is no longer T from the maximum, it's T plus 1. Because here is, yeah, you have to add the number of matching in here, yeah, and plus here. Okay, so you have violating this condition, yeah, the first condition. Okay, so this is the proof that F contain no breach. Okay, furthermore, if F has a connectivity 1, yeah, so F has a cut vertex and suppose F has no bridge. Yeah. And then W, let's W is a cut vertex of F belonging to N block. Yeah. So this is suppose if you have F is connectivity 1, that means by removing one vertex, you will destroy the connectivity, yeah, of graph. So you can assume that, okay, the graph is like this, for example, yeah? Or can be, yeah, like this, yeah, or, yeah. So if you remove one vertex here, you destroy the connectivity, yeah. Okay, but there is no bridge because we already shown this one. Okay, and this is the end block. Yeah, this adjacent to X, and it is here that if this is W, okay, not X, yeah, W, this is the cut vertex, then F minus F1 is any end block of F containing W. So this is, okay, we may assume this is F1. And then the remaining here is actually union of the remaining blocks. So can we have several blocks here, right? Okay. Okay. And here it shows that neither F1 nor F2. So the remaining we call it F2, yeah? So this is F1 and this is all F2, yeah? And F1 nor F2 are edges, yeah? It's not possible. If you have this is on the edges like this, then okay, so it's not possible, yeah? So it must be not edges. And so that both have edges not incident to Y. So in fact, we have edges here not incident to Y here, to W here, the edges in here, in F here, F1. And since F satisfy the second condition, then if you remove W, if you remove W from F, then they have a T matching. Yeah. So that F I can be 1 or 2, yeah, containing, yeah, here containing Ti matching, and then this is T1 matching, and then here is also T2 matching. Yeah. Okay, so together you sum up, you have a T matching. Yeah, you have a T matching. Yeah. Okay. So since F is satisfying property 2 and 3, yeah, then here each T1, Ti is at least 2. Yeah, the matching that you have in F1 and F2, at least 2, cannot be 1. Yeah, yeah, this is the matching. Yeah, here and here, and also here. Yeah, at least 2. Since the Fi cannot be a triangle tree with 3 vertices. Okay. And by this consideration, we can summarize that here we have theorem 2. If F1 is belong to this Ramsey minimum graph, and F2 is belong to this Ramsey minimum graph, then the union, if this is belong to T1, this is belong to T2, the union here belong to T1 plus T2. And then the dot product yeah, F1 and F2 also belong to T1 and T2. Okay, the one that we already shown. And then here, if F have a connectivity 1, so that means F if this kind of graph, yeah, can be like this, yeah, and so on, yeah, connectivity 1, then F is belong to this Ramsey minimum graph, then we can partition T into T1 and T2 such that the F, yeah, must be of the form V1 dot V2, with P1 is in this Ramsey minimum graph, and the P2 is this Ramsey minimum graph. Yeah. And then this is the important one, the corollary. Yeah. Let's T naught is a fixed integer, positive integer, and H here is a collection or a set of all a graph F, which is two connected. Yeah. Okay, theorem 1 is connectivity is 1. So now in corollary, we consider the two connected. Yeah. Okay. If F is two connected and F is belong to this Ramsey minimum graph, yeah, the set of Ramsey minimum graph, then this is the characterization. Okay. Then the set of 2K2, T no K2 is equal H. It is the set. And then L. L is this kind of graph, yeah, produced by dot product and union, yeah. And then this is the one that we excluded. This is T0 plus 1 K2, the disconnected graph, yeah, the only disconnected graph that we have in this Ramsey minimum graph. So the characterization of this Ramsey minimum graph consists of H. This is a set of all graph which is two connected and Ramsey minimum graph, yeah. And then L is already definite, yeah. You know exactly the same here, yeah. Connected by 1 and formed by this, yeah. So, yeah. And the last one is disconnected graph, T0 plus 1 K2. So it's clear that now you may question what kind of graph belong to this. Yeah, belong to this set of Ramsey minimum graph. Okay. In the previous slides, we already shown that each cycle, odd cycle, belong to this. Yeah. 2K2, TK2, right? And now, yeah, the corollary here, if we have G be a graph with its block B1, B2, and BK is an odd cycle, then, yeah, then each here is at least 5 vertices, yeah, and then you have this kind of formula, yeah, satisfied. So if you sum all the number of vertices in this cycle, yeah, -1, yeah, and then you divide by 2 each one, and then you call it T here because all odd cycle, right? And so you have this kind of sum, yeah. Then G will be in this graph. Yeah. Okay. So suppose if you have, this is 5, and then you join, yeah, which is a form a block, yeah, and then you join here with, for example, like this, you know, this is 7, yeah, and then you join again here. 1, 2, 3, 4, 5, yeah, and then you have here 1, 2, 3, 4, 5, yeah, and so on. Suppose here you have this one, yeah, then okay, this graph belong to Ramsey 2K2, comma T. T is here, yeah. So how many here? 5, this is 2, yeah. 5 minus 1 divided by 2 is 2, yeah. And then this is 3, this is 2, and this is 2, yeah. So you sum up, yeah, you have 9. So 9 K2. Okay. Yeah. So that means, okay, let's check here to avoid this is red. Yeah. So you may have this is red, yeah, and this is red, right? Yeah. Oh, sorry. 2K2. Yeah. Oh, okay. Oh, let's say here. 2K2, no red. So you have like this, for example. Okay. To make many edges, yeah, in red, yeah. Okay. If that happened, then you have how many blue edges in independent? Yeah, independent edges in blue. So you have here 1, 2, yeah, and then 3, yeah, 4, 5, yeah, 6, you know? And then what else here? We have this. We have 2 here. We have 2 here. We should have 3 here. How do I have 3? One, 2, 3, 4, 5, 6, 7, 8. One more. Sorry. We should have like this. And instead of here, we have this one. We have this one, right? Yeah. Here, instead of this one, we have this one. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So if you avoid red 2K2, you will have blue 9K2 for this guy. Okay. Okay. So if you have block, this is, we call it block. Yeah. There's a cycle. Yeah. Block is cycle here. Odd cycle. Okay. Then you have this graph. Okay. From cycle, yeah, you can obtain many kind of graph belonging to this one, right? Yeah. Okay, so a large number subset of graph that you produce, yeah, for 2K2, T2. This is some of the examples. Yeah, this is with the connectivity 1. At least 1. Yeah. So here, when you remove one vertex here, will disconnect. Yeah, remove this one, it will disconnect. So yeah. Okay, so you have many variety of graph for this Ramsey graph for 2K2, 8K2. This is only 8K2, yeah? We have 1, 2, 3, 4, 5, 6, 7. Then we Okay, this is only with pentagon, with 5 vertices in the cycle. You may have 7, you may have 9 combination between these cycles as well. Yeah. Okay. And this is another graph which is connectivity is less than 1, less than or equal 1. Okay, so this graph is connectivity is 0. Where sorry, this is connectivity is 1, still 1. Sorry, yeah. Okay, because we should remove this one, and then here you have you increase the number of components of this graph. Okay, so you have plenty of graph, yeah, of Ramsey minimum graph for this time. What about the graph with connectivity 2? Yeah, okay. Remember in the theorems here, in the corollary here, yeah. Let's say here, yeah. So this characterization, yeah, is only completed by H. L we know already, yeah. Yeah. The structures of the graph. This is formed by dot operation and union, yeah. For smaller graph, Ramsey minimum graph, yeah. And then this one is known already. This is only one graph, and each, yeah, is a 2 connected graph. Yeah. Okay. So back again to here. Then this set is completely determined by its 2 connected members. Yeah, 2 connected graphs. Yeah. Even this could prove very difficult to find, for example. Yeah. So far we cannot classify all 2 connected members for this one. Here we just give some of them. Each one, for example, like this. This is H2. Yeah. H1 is belong to this one, and H2 belong to this. And we have many others. Okay. But if we specify the TK2, yeah. So if we fix T, for example, TS2, you have this. TS3, yeah, is shown, we have this. TS4, we only have this, and so on. Okay. And what are they? This graph, yeah, is here. G1, G2, G3. This is this graph that's shown by both for this Anderson Rosu in 1981. Yeah. Okay, so this is G4. We have 1, 2, 3, 4, 5. G4, yeah. G4 is in here. Yeah. This is G4. Yeah. Okay. Okay, but it's okay, different formula, yeah. Different graph here. So okay. And this is G5. All these graphs are G5. Yeah. And now for the question here, what is the maximum order and size of members of this? Still unknown. Yeah. The maximum order. Yeah. Let's say if F is belong to this set, to K2, TK2.
what is the maximum order and the maximum size of these members? Okay, it's rather large upper bound is given already by Paul and Ross, Rodri, and Shaw, but this is very large. Okay, so this example give you a demonstration the difficulty of finding an explicit characterization of set of the Ramsey minimal graph for a given G and H. And it will be extremely valuable to complete such a characterization for a special pair of this. Okay, you may try. You fix T here and you find characterization of 2K2, TK2. One of our students able to do that by fixing, oh, okay. This is a different path, yeah? Okay, this is 3K2, P3. Yeah, this is another example, yeah. Okay, this is one of my student, my bachelor student, a couple of years ago, yeah, able to characterize, yeah, all graph with belong to this set. 3K2, this is 3K2, and then P3, yeah. And this graph is finite, yeah. Okay, I'll give you, this is the property, the necessary condition of graph F, yeah, belonging to this Ramsey minimal graph, so must satisfy this 5 condition. Yeah, instead of removing 1 vertex, we remove 2. Yeah, yeah. If you remove 2 vertices, yeah, you will have P3. Yeah, and then if you remove 1 vertex and a cycle, 1 vertex cycle, a triangle, not cycle, it's also you have a P3. Or if you're removing 3 triangle, you will have P3. Or the last one here, the fourth one, if you remove any subgraph F of 4 or 5 vertices, yeah, in F, you will always P3. And the last one, every vertex in F contain some P3. Okay, and by using this property, yeah, this is no proof. Probably I just skip it, yeah, and then we can characterize, yeah, and also by using this lemma. And this lemma is also very important. If F is belong to this Ramsey minimal graph, then this must be whole. Yeah. So if you remove 1 vertex from F, you remove 1 vertex from F, then you have 2K2, P3. Yeah. So there will be either 2K2 or P3. Yeah. And here, if you remove 1 triangle, yeah, you will have this one. Okay, so this is reduced, yeah? Okay, let's have a look here. This is 3, it's reduced by 1, yeah? Yeah. So here that means if you remove 1 vertex, yeah, you will have subgraph of Ramsey minima of 2K2, P3. Implies that means like that, yeah. Okay. So we use these 2 facts, yeah, theorem and lemma, and we can show here if F is this Ramsey minimal graph, then F minus 3, yeah, any vertex, and F minus edges of triangles will contain some Ramsey minimal graph of 2K2 now, comma P3, by removing either one vertex or the edges of triangle. So the proof is directly from this lemma. I already mentioned the lemma, the previous lemma, this lemma. Okay. And by using this fact, we will characterize all 2K2, 3K2, comma P3. Before that, we have already characterization by Mangersen and Ockerman, but this is 2K2, not 3K2, yeah? 2K2, comma P3. This is consists of only these three graph, yeah? C4, C5, and 2K2. Yeah. And if G is in this graph, in this Ramsey minimal graph, then G union P3 is also Ramsey minimal graph, but now is in 3K2, not 2K2, but 3K2. Yeah. So here, and here is a Ramsey 3K2 P3. Okay. And furthermore, we have that we can show that this is necessary and sufficient condition. Yeah, if having G is in 2K2, then the union by P3 is also Ramsey minimal. Yeah. And then if F is disconnected graph in this graph, then at least one component of F must isomorph to P3. So if you have more than one components in F, then must be one here isomorph to P3. Yeah, this is P3. Yeah, isomorph to P3 here. Okay. And then this theorem classify all disconnected graph in 3K2, comma P3. This is which are only these three. Yeah, C4 union P3, and then C5 union P3, and 3P3. And now we characterize it all connected graph. First, we show there is no tree in this graph, in this Ramsey minimal graph. So that means every connected Ramsey minimal graph of this type must have a cycle. Yeah. And now the only cycles which are Ramsey minimal graph is C7 and C8. Yeah. Okay. And suppose that if such Ramsey minimal graph not isomorphic to cycle, then we will have the largest cycle in F is in between 3 and 8. Can show like that. And then now we can find, yeah, how many graph with C3 is the largest cycle, and how many graph with C4 is the largest cycle. Yeah, some C5 in the larger cycle. Yeah, we prove that there is no one with this property. So this is C up to C5. What about if the largest cycle is C6? Then we have this kind of graph. We have 5. Yeah. And then 7, 8. Yeah. If we have C7, that means we only have the cycle of C7. Yeah. So it's no other graph. Yeah. And also CH. Yeah. Okay. So here the last theorem say that all connected graph, yeah, in this set are only C7, C8, and this graph. The one that already drawn in the previous slide. Okay. And together with the disconnected, with this disconnected graph, so we have this one. So this is together with 3P3, and then C4 union P3, and C5 union P3. Okay. And this is the last slide. I just give some references for additional results if you are interested in seeing the development of this topic. Yeah. So in fact, yeah, for matching, we able to class to characterization or to derive the sufficient necessary condition for matching comma H for any H. Yeah, so you can see from this slide, from this paper. Yeah, and if we specify the H, yeah, if we fix, for example, here we fix M, this is 4, and this is P3, yeah, and then we can derive all the graph belonging to this set. Yeah. And here is also classification for all unicyclic Ramsey minimum graph if H is P4. Okay, so this is the recent result. Okay, I must to stop my presentation now. Okay, terima kasih Pak Andi. Yeah.
All right, thank you very much, Professor Edi Tribaskoro. Can we give a virtual applause? Guys, okay, thank you very much for the excellent materials, and thank you for answering the student questions. Is there any other questions that the student would like to ask to Professor Edi Tribaskoro regarding the material today, the Ramsey minimal graph? Okay. Is there any other query?
Oh, somebody have a coffee break. Yeah. We have a coffee break now. Yeah.
All right. Yeah. Or the questions already answered in the chat room, right?
Okay. When you got interested in doing Ramsey, so you just you may read our current papers. Yeah, I just give it in the last slide. Okay.
All right. Thank you, Professor Edi. So Before we close our class, our lecture today, we want to take a picture. So I asked the students and also all of the participants. I see here not only students come to the room. Okay, so I would like to ask you to open your cameras, and then the committee will take a picture for us. Ma'am Prita, who will take the picture?
Okay, wait a minute. Okay, so for the first slide, everyone smile. 1, 2, 3. Okay, and in the next slide. Okay, everyone smile. 1, 2, 3.
Okay,
Okay, and the last
page.
one. 1, 2, 3. Okay, thank you very much, everyone.
Oke, ya, terima kasih semuanya. Thank you.
Thank you, Professor
Alright.
Edi.
Ya, ya, oke.
All right, thank you everyone. We
Ya,
can
bye-bye
next lecture.
from
Thank you,
now.
Mr.
Ya,
Professor Edi Baskoro. Okay, have a nice day. Stay healthy.
oke, thanks a lot.
All right, we can leave the room, I think. Okay, thank you very much.